This tells us we got a linear triatomic gas, 4 moles of it, and the vibrational modes are frozen out. It also tells us the molecular mass, the mass of each molecule, and the average translational speed. And we want to know what the temperature is. Any thoughts on how those are related? If what we know is something about the translational speed of one molecule, and we want to know something about the temperature, what might relate those? If we know the average speed of a molecule and we want to know the temperature, how are those related to each other? What would be some concepts that tie together the average speed per molecule versus the temperature? Or why would those be related in the first place? Somebody just mentioned it in the chat just a few minutes ago, the idea of equal partition of energy. What do we mean when we talk about equal partition of energy? What is equal partition in the first place? What do we mean when we say energy is experiencing equal partition? What do you mean by 3 factors? Well, what equilibrium? What do we mean by equilibrium here? That's not exactly what equal partition means. The equal partition theorem is the statement that if temperature is the same everywhere, then energy per mode is the same. That is, if you got any 2 or more substances that are all at the same temperature, then they all have the same energy per mode, at least on average. That's all equal partition is saying. In the sense that the thermal energy is evenly divided amongst all the modes. It splits up so that all the modes have the same amount of energy on average. This also tells us that the energy per mode depends only on the temperature. And in particular, energy per mode is proportional to temperature. In other words, it equals something times the temperature. This is all proportional means. If we say 2 quantities are proportional, that means that one of them can be written as equal to some constant times the other. And what is that constant of proportionality here? What multiplier turns temperature into energy per mode? Yeah, half of Boltzmann's constant. So half of Boltzmann's constant, kB over 2, is the conversion factor that converts temperature in kelvins to energy per mode in joules. Boltzmann's constant being measured in joules per Kelvin as shown down here. 1.38 times 10 to the negative 23rd joules per Kelvin. So that's the relationship between energy per mode and temperature. If we can find the energy per mode, we can solve for temperature. But we don't have energy per mode. We have average speed of a molecule. Is there any way we could use the average speed of a molecule to find the energy per mode, or equations that might relate those together? In particular, if we're talking about energy and we're dealing with speed, what kind of energy is related to speed of the molecule? I mean, this does technically count as thermal energy in the sense that it's related to temperature. But thermal energy is more of a macroscopic description if we're looking at the big picture, the whole thing. Here we're looking at the behavior of individual molecules. So what kind of energy is associated with how fast a molecule is moving through space? Rotational kinetic energy would be associated with how fast a molecule is spinning. But here we're not talking about how fast it's spinning, we're talking about how fast it's moving through space. So what kind of energy is related to how fast an object is moving through space? Yeah, the translational kinetic energy. So if we know the average speed of the molecule, we can find the translational kinetic energy. And then we can relate that to the energy per mode. So I think our general scheme here is going to be, since we know the average speed of a molecule, we can use that to find the kinetic energy translational of a molecule, tying those together. And then we can use that to find the energy per mode, or at least connect it to the energy per mode. And once we know the energy per mode, we can use that to find the temperature using the idea of equipartition, that the energy per mode is half of Boltzmann's constant times the temperature. And this I find is often a very useful way to start a problem. If you just have no idea where to go, write down what you know, maybe a list of several things you know, and what you're trying to find. And see if you can come up with a series of steps that link them together. Even if you don't know how what you know and what you want are related directly, figure out what else can you figure out from what you know, or what other information is related to what you're trying to find, and see if you can set up a series of links, even if they don't seem to connect directly. And what we now have is essentially an outline for how to solve this problem. We can use the average speed of the molecule to connect to the translational kinetic energy of the molecule, use that to connect to the energy per mode, and use that to connect to the idea of temperature. And maybe we'll do this one step at a time, or maybe we can use this logical chain to construct one big equation. Depends on the circumstances and how we want to go about this. Any questions on that outline so far? So let's see if we can write out some equations to connect these together. Because once we've set up a conceptual idea of how these are related, we want to turn those concepts into equations that we can solve. For instance, what equation or formulas might relate the speed of the molecule to the kinetic energy of the molecule? How is speed related to kinetic energy? Yeah, go ahead.
1/2 times the mass times the velocity squared.
Yeah, that should work. Kinetic energy translational is half the mass times the speed squared. And we know the speed, 500 meters per second, and we know the mass, 8 times 10 to the negative 26 kilograms. So we can find the kinetic energy of that one molecule. And we could do that numerically right now, but I think it might be more useful to leave this as just a formula in terms of variables. You can always fill in the numerical values for the variables at the very end. But I would generally recommend leaving things in terms of variables when possible, because that often makes it much easier to simplify. And if you save all of the numerical calculations for one big step at the very end, that reduces rounding errors and reduces possibility of making arithmetic mistakes. What about this next step, the relationship between kinetic energy of the molecule and energy per mode? How many modes are we talking about if we're dealing with the translational kinetic energy of the molecule?
3.
Yeah, because no matter what kind of molecule it is, like this is a linear triatomic gas, we could figure out how many modes it has in total, but we don't really care how many modes it has in total. We're just looking at the modes that are related to translational kinetic energy. So there are 3 modes of translational kinetic energy in that molecule. And what's the energy per mode?
1/2 kBt.
Yeah. So the 3 modes would have 3 times 1/2 kb times temperature. So the translational kinetic energy of one molecule should be 3 times the energy per mode, because there are 3 modes that we care about as far as translational kinetic energy is concerned. And we now have 2 different ways of writing the translational kinetic energy of one molecule. The translational kinetic energy of one molecule is 3 times the energy per mode. And also the translational kinetic energy of one molecule is 1/2 mv squared, the usual formula for kinetic energy. If we have 2 formulas representing the same quantity, what can we do with those 2 formulas?
Set them equal to each other.
Yeah, we can write that as one of the formulas for translational kinetic energy of one molecule equals the other formula for translational kinetic energy of one molecule. That is, the translational kinetic energy of one molecule is 3 times the energy per mode, because 3 of the modes count as translational kinetic energy. Any questions on that so far? And what are we trying to do here? What's our ultimate goal in this problem? Yeah, ultimately we want to find the temperature. We now have an equation with temperature in it, and I think we know all the other values. We're given the mass, we're given the speed, and Boltzmann's constant is just a universal constant. So algebraically, how would you isolate T here before we even fill in any numbers? How would you solve this for T?
Divide both sides by 3 times kb over 2.
Yeah. If we divide both sides by 3 kb over 2, then on the right side, those cancel out. We're left with just temperature. And on the left side, what happens when we divide this by 3 kb over 2? What's left there? Or does anything reduce?
The over 2's cancel out.
Yeah, we've got an over 2 in the numerator divided by another over 2 in the denominator. So those divided by 2's cancel out. You could also think of that as a times 1/2. So the times 1/2's cancel out. We're left with mv squared divided by 3 times Boltzmann's constant. So it looks like that's all that's left. Temperature is mass times speed squared divided by 3 times Boltzmann's constant. So we now have not just a number, but a formula for the temperature in terms of the mass and speed of individual molecules. Any questions on that so far? And now if we actually fill those in, we've got mass 8 times 10 to the negative 26 kilograms times speed 500 meters per second squared divided by 3 times Boltzmann's constant, which is 1.38 times 10 to the negative 23rd joules per Kelvin. And to simplify this a bit, first of all, I find it's often useful to write everything in scientific notation. Like 500 is 5 times 10 squared. And that actually is going to make it a lot easier to simplify things, I think. Because what do you get when you square 5 times 10 squared? If you multiply 5 times 10 squared by itself, what do you get? If you got 5 times 10 squared times 5 times 10 squared, if we rearrange those a bit, what's 5 times 5? And 10 squared times 10 squared? Yeah, or I would just leave it in scientific notation, 10 to the 4th. Exponents are a lot easier to work with. Like if everything's in terms of 10 to a power, that's a lot easier to work with than writing out all the zeros. Like 8 times 10 to the negative 26, I wouldn't want to write that out as 0 point lots and lots and lots of zeros followed by an 8. I would just write it as 8 times 10 to the negative 26. So 8 times 10 to the negative 26 times 25 times 10 to the negative 4. And what are the units there? If you've got kilograms times meters squared per second squared, what does that combine to? What do we call kilograms meters squared per second squared? Where have you seen kilogram meters squared per second squared before? Yeah, that is in fact the definition of joules. Joules means kilograms times meters squared per second squared. So anytime you see joules, you can expand that to kilogram meters squared per second squared, or alternatively, anytime you see kilogram meters squared per second squared, you can abbreviate it as joules. Joules is just shorthand for this cluster of units. So kilograms meters squared over second squared is just joules. So the whole numerator just becomes joules as the units. And then in the denominator, we've got 3 times 1.38 times 10 to the negative 23rd joules per Kelvin. And as far as the units are concerned, what happens when we take joules and divide by joules per Kelvin? Yeah, joules cancels out. And we're left with 1 over kelvins, which just flips and becomes kelvins. So we end up with units of kelvins, which is what we should expect because we're talking about a temperature. And let's see what that looks like in the end. In the numerator, we've got 8 times 25. That's just going to be 200 because I know 4 times 25 is 100. So 8 times 25 would be 200 times 10 to the, and if we combine these, in fact, if we combine all of these, all the 10 to the whatevers, so ignoring the 8, the 25, the 3, and the 1.38 for now, what do you get if you combine 10 to the negative 26 times 10 to the negative 4 divided by 10 to the negative 23? Or how would you combine those? How do exponents combine when you're multiplying or dividing the bases? Yeah, you can add the exponents. So we've got negative 26 plus 4, that's negative 22. We're also dividing by 10 to the negative 23. What happens when you're dividing by an exponential? Right, we just subtract. So the overall exponent is going to be negative 26 plus 4 minus negative 23. Negative 26 plus 4 is negative 22. Minus 23, that's the same as plus 23. And negative 22 plus 23 is just 1. So all those exponentials just turn into 10 to the 1. We've still got kelvins as the units. And we've also got divided by 3 times 1.38. 200 times 10 is just 2,000. So it looks like we're left with 2,000 divided by 3 times 1.38. And at this point, that doesn't look like there's any more easy simplifications to do. 2,000 is not a nice neat multiple of 3 or 1.38. So I would go ahead and type that into a calculator. But note that this whole thing only requires one final calculator step at the very end. 2,000 divided by 3 times 1.38. And make sure you're putting the 3 times 1.38 in parentheses because we're dividing by that whole thing. And I'm getting about 483. 483 Kelvin. So that should be the final temperature, or sorry, the temperature of this gas. It's not so much final temperature because it's not changing. 483 kelvins is just the temperature of this gas. And again, note that we started by just listing out what we know, what we're trying to find, form a logical list of links between those so we can get from what we want through maybe several steps to what we're trying to find. Write out some equations for each of those logical leaps, combine them into just one big equation, and then we can solve that for temperature, which is exactly what we now have. Any other questions on that so far? All right, then let's try out the other problem on this practice quiz as well. Let me clear off that so far. And there's some space. By the way, in the previous example, let me back up to that for a minute. In the previous example, one other thing I wanted to mention, what information from this statement did we not end up needing at all? What information did we not actually have to use? Uh, 6n minus 5 equation, what would the 6n minus 5 equation tell us? Uh, 6n minus 5 doesn't tell you the number of molecules, although this does tell, the problem itself tells us the number of molecules. Specifically, the number of molecules was 4 times Avogadro's number, 4 moles of molecules. Why did we not need that information at all? Why did the number of molecules not become necessary here? If we go back to the process we just did, going back through this chain of logical leaps, did any of the steps we took have anything to do with the number of molecules that were present? Yeah, we didn't really use that information, right? We were given information about the behavior of an individual molecule. We were trying to find the temperature, but based on the equipartition theorem, the energy per mode is all about the temperature. So temperature is directly related to the energy of one mode in a molecule. And therefore you can relate the temperature of the whole substance to the behavior of one individual molecule or one average molecule. So you don't really need to know how many molecules there are in this case. If you know something about the behavior of individual molecules, which we do, you can use that to get information about temperature. It doesn't matter how many molecules there are. We can just look at the behavior of individual molecules. On the other hand, if we were given information about the whole substance, like if we were told the thermal energy of the whole thing, we'd need to pare that down to energy of individual molecules and individual modes. So in that case, the number of molecules would be important. But in this case, we don't have information about the whole thing. We have information about individual molecules, and that's what's important. Likewise, we didn't really need to use the fact that it's a linear triatomic gas. That information would tell us the total number of modes of a molecule. But we didn't really care about all the modes here. We only needed to worry about which modes. What were the only modes we actually needed to use in this situation? Yeah, specifically those three translational kinetic energy modes. The molecule certainly has other modes. It has, since it's linear, it presumably has two rotational modes and no vibrational modes because those are frozen out. So the molecule has 5 modes, but the only ones we care about are the 3 translational modes, because what we care about is how to link the temperature to how fast it's moving. The problem didn't give us information about the total energy of the molecule. It just gave us information about the translational speed. That directly ties into the translational kinetic energy. And every molecule has 3 modes of translational kinetic energy because it's able to move in 3 dimensions. So it doesn't really matter what other modes it might or might not have. It's able to move in 3 dimensions, so it's got 3 modes of translational kinetic energy. And those are the only modes we care about in this context because we know something about its translational speed. Any other questions on that one? All right, then let's go ahead and take a look at that next one as well. And again, let me clear this out. So here we have a nonlinear triatomic gas. We've got 3 moles of it. We know it's frozen vibrational modes, so it's only got the translational and rotational. Also 2 moles of a diatomic gas that does have vibrational modes. Put them in a thermally insulated container, so presumably this is a closed system. And they start off with apparently different temperatures. We know the temperature, the starting temperature of the triatomic gas. It doesn't tell us the temperature of the diatomic gas, but it does at least tell us the rotational kinetic energy per molecule. And we want to know what's the temperature of the system at thermal equilibrium. So presumably they start at different temperatures. They're going to meet somewhere in the middle. We want to figure out what that equilibrium temperature is. So again, let's list out what we know, what we're trying to find. Certainly what we want in the end is final temperature at thermal equilibrium once both substances reach the same temperature. But what information do we know that might be relevant to that? What's our known information here? Do we have any information about the system that might be relevant to the final temperature at thermal equilibrium? Or alternatively, we might be able to, oh yeah, we could start by listing out the number of modes, right? The diatomic gas we know has 5 modes because which modes in particular? Also, for ease of reference, let's say the 3 moles of nonlinear triatomic gas is sample A, and the 2 moles of diatomic gas is sample B. just so we can refer to them more easily, more quickly. Yeah, so let's list out their modes. We have, we know A has, since A has, it's nonlinear, it's triatomic. So what modes would, or which modes would we expect there? If we wanted to count up all the modes per molecule. First of all, it's able to move. So how many translational modes does it have? Yeah, anything that's able to move in 3 dimensions has 3 translational modes. Does it have any other modes? What other modes might be involved other than just the ability to move around in space? What's another way it could be moving other than just traveling through space? Yeah, we'd have rotational modes as well. And if it's nonlinear, how many axes can it rotate around? How many dimensions is our universe? Yeah, last I checked, we live in a 3-dimensional universe. So we should expect an object to be able to rotate around 3 dimensions. Like for instance, this pair of pliers here can rotate around the x-axis, can rotate around the y-axis, and can rotate around the z-axis. So this object has 3 rotational modes. So 3 translational modes, its ability to move through space, and 3 rotational modes, its ability to spin. And it could also have vibrational modes, but it specifically says here the vibrational modes are frozen out. So 6 modes per molecule. What about sample B? How would we count up the modes for sample B? Which ones would we want to include there? If it's a diatomic gas. Is the diatomic gas able to move? Yeah, it's going to have translational and rotational. As a diatomic gas, it can move in 3 dimensions, so there's 3 translational modes. But if it's diatomic, that means it's arranged in a straight line. So instead of having some nonlinear shape, it's just everything arranged in a straight line. How many dimensions can just a straight line rotate around? If you just got like atom in a diatomic molecule, yeah, only 2. You can rotate around the z-axis like this. You can rotate around the y-axis like this. But if you try to rotate around the z-axis, you're essentially just not really changing anything. If this is truly just a single straight line, then nothing's really changing if you spin it around its own axis. So that doesn't count as a separate rotational mode. A linear molecule, including any diatomic molecule, is only going to have 2 rotational modes. But it also has vibrational modes because it specifically says with active vibrational modes. So what would you expect the, or how many vibrational modes would you expect it to have? Yeah, that should be 2. If you got just 2 atoms in the molecule, then within the molecule, they can be vibrating against each other. And that counts as 2 modes because within that single dimension of vibration, they're just vibrating in a 1-dimensional space, the 1-dimensional bond itself. They've got kinetic energy because they're in motion, and they've got potential energy because they're interacting with each other, but only in that 1 dimension. It's like they're connected by a single tiny spring. So that would be 1 kinetic energy and 1 potential energy modes And we would just lump those together as 2 internal vibrational modes. And that's it. So we got 3 + 2 + 2, 7 modes per molecule. And that's the most you can expect for a diatomic molecule if all the modes are active. So we at least know the modes per molecule. And that's going to tie into the final temperature because in general, ignoring the information we have, in general, if you have 2 objects at different temperatures and they're approaching thermal equilibrium, think way back to the very beginning of the quarter. What sort of approach would we use if we wanted to find the final temperature as they interact with each other? What's usually a good approach to finding the final temperature as 2 objects exchange heat? I don't think we need to worry too much about state here, at least not phase change. Or do you mean, what do you mean by state here? Well, the phase is not changing, I don't think, because it specifically tells us that these are both gases. It doesn't really say anything about any boiling point temperature, so I think we should probably just assume they're both gases the whole time. It probably should have specified that, but I think we can probably assume these are both gases the whole time. But if there's no phase change, what's the only type of energy that's changing here? Bond energy would be associated with a phase change, but what kind of energy is associated with temperature? Yeah, thermal energy should be it here. If they're both changing temperature, presumably the hotter one's getting colder and the colder one's getting hotter until they meet somewhere in the middle. So that suggests that thermal energy is changing for both substances. So if we wanted to write out conservation of energy, we'd have change in thermal energy for object A and change in thermal energy for object B. Those are the only changes that are happening. And what should we expect those changes to add up to here? Does this problem tell us anything about what we should expect the total change in energy to be? Is there any heat or work entering or leaving the system? Or how could we tell? Yeah, it tells us this is in a thermally insulated container. So right, we should treat that as a closed system. Thermally insulated means there's no heat entering or leaving. And this doesn't say anything about a piston, so I would assume there's no work entering or leaving either. So we can assume this is a closed system and the changes in energy have to add up to 0. More generally, we'd say the changes add up to heat plus work, but there's no heat because it's thermally insulated, and I would assume no work because it doesn't tell anything about pistons or expansion or contraction. So we know these thermal energy changes have to add up to 0. We also know something about number of modes. Do you have any information relating thermal energy change to number of modes? What's a useful formula for thermal energy in terms of number of modes? Or do you have any formulas relating thermal energy to modes? What's MPM there? Oh, modes per molecule. Okay. Yeah, that should do it. Yeah, number of modes, which is implied to be number of modes per particle times 1/2 times n times r times, and since there's a delta here, I'll write this as nr delta t. And note that in both cases, for sample A and sample B, we know the number of moles, 3 or 2. We found the number of modes, so that's all good. R, of course, is a constant, and delta T can be written as final temperature minus initial temperature. So if we fill in that formula for both of these substances, for A, we've got number of modes. How many modes does sample A have per particle? Sample A has how many modes per particle? Yes, that was 6. So for this formula, number of modes over 2, we'll write 6 over 2 times N, which is, for sample A, we've got 3 moles, times R, which I'm just going to leave as R for now. We can fill in the value later, times delta temperature. That'll be T final A minus T initial A. Plus, and then for object B, we've got the same idea, number of modes over 2, except for B, number of modes is 7. So 7 over 2. Number of moles looks like we've got 2 moles times R times delta temperature. So T final B minus T initial B. And again, those have to add up to 0. So this at least gives us an equation describing how these terms are related to each other. Any questions on that so far? On the setup for that conservation of energy there. And it looks like we still have a lot of variables here that we don't have numerical values for yet. Do we know any of these temperatures? Do we know anything about the initial temperatures or final temperatures of any of these? Yeah, it tells us the initial temperature for sample A. And by the way, it's okay to fill in more of the known information as you go. Like if you're trying to work out how what you know is connected to what you want, and you realize there's another piece of information you need, but then you realize that information is provided, go ahead and fill it in the know list. We know that like I just filled in, we know total energy is conserved. We know, as you say, initial temperature for A is 373 Kelvin. That's provided right here. So we can fill that in. Initial temperature for A, 373 Kelvin. We can fill that in right now. Do we know anything about the final temperatures? What does it mean by thermal equilibrium in the end result? Yeah, we don't know what the final temperature is, but yeah, they got to have the same final temperature because thermal equilibrium means everything has reached the same temperature. If we wait for thermal equilibrium, that means we are waiting until they reach the same final temperature. And what that means in terms of the equation is we don't need to separately label T final A and T final B. It's the same T final, so we can get rid of the A and B subscripts. It's just T final and another copy of the same T final. The same value variable just showing up twice in the equation. So T final, which is what we're trying to solve for, R, which is a value we can plug in if we need to. What about the initial temperature of object B? Do we know anything about the initial temperature of B? Or do we have other information we could use to find it? Does this problem tell us anything about the initial situation of sample B? Yeah, it doesn't directly tell us the temperature, but it tells us the average rotational kinetic energy of a diatomic gas molecule. So we could use that. We could use the fact that one molecule of B has rotational kinetic energy 8.28 times 10 to the negative 21 joules. Is there any way we could use that rotational kinetic energy to find the temperature? Or how could we relate the energy per molecule to the temperature of the substance? Think back to what we were doing in the previous problem. How did we relate the energy per molecule? Yeah, going back to 1/2 kBT, the energy per mode. So if we repeat the same sort of process we did in the previous problem, we know the energy per mode is 1/2 times Boltzmann's constant times temperature, half of Boltzmann's constant times temperature. And in terms of modes, we're talking about the rotational kinetic energy. So we only need to care about the rotational modes. How many rotational modes does one type of B molecule have here? Right, should be 2 because it's a linear molecule. Diatomic is automatically going to be arranged in a straight line because if you just got 2 points, they've got to be on a straight line with each other. So each type B molecule has 2 rotational modes. So we can say that the kinetic energy rotational is 2 times kb/2 times temperature. In other words, just kb times temperature. The 2's cancel out. Which means if we want to find the temperature, we can set kb times temperature equal to that rotational kinetic energy. And how would you solve for temperature there? What's the opposite of multiplying by Boltzmann's constant? Yeah, if we just divide by Boltzmann's constant, that should give us the initial temperature of object B. So I think we should be able to use that then. We know the rotational kinetic energy per molecule. If we divide that by Boltzmann's constant, then that should give us the initial temperature of sample B based on the equipartition theorem. So if we fill that in, we got 8.28 times 10 to the negative 21 joules. We're dividing by Boltzmann's constant, which is 8.31 times 10 to the negative 23rd, I think. Is that right for Boltzmann's constant? We just had it up here. Oh, I was thinking of R for some reason. That's 1.38. Just had the digits backwards. 1.38 times 10 to the negative 23rd joules per Kelvin. So dividing those, and before we even hit the numerical values, what's 10 to the negative 21 divided by 10 to the negative 23rd? Almost. We're subtracting the exponents. Negative 21 minus negative 23rd. What's negative 21 minus negative 23? Yeah, 10 to the positive 2. And again, joules and joules cancel out. We're left with 1 over Kelvin, which is just Kelvin, which is good because that's what temperature should be measured in anyway. And all that's left is 8.28 divided by 1.38. I'm not noticing any immediate simplifications there, so time for a calculator. 8.28 divided by 1.38. Oh, that happens to be exactly 6. So 6 times 10 squared. In other words, 600 Kelvin. So that information does indirectly give us the initial temperature of B. The problem didn't directly tell us the initial temperature, but it gave us enough information about the molecular behavior that we can connect that to the actual initial temperature. So we now do know the initial temperature of B, and we can fill that in our conservation of energy equation. Initial temperature of B, 600 Kelvin. And at this point, it looks like T final is the only unknown left in this entire equation. Any other questions on that so far? All right, so let's see if we can use algebra to solve this for T final. Because once we set up an equation and there's only one unknown left, then the rest is algebra anyway. Before we even start isolating T final, is there any way we could simplify this or anything we could do to cancel something out so we don't have to worry about it at all? Anything that shows up in every term? Are there any factors, any multipliers or divisors that shows up in every term here? Yeah, we definitely have a times R in every term. And we could get rid of that, since it shows up in every term anyway, we may as well get rid of that by dividing both sides by R. If we just divide both sides of this equation by R, on the left side, we can distribute that. The first term divided by R plus the second term divided by R, the R's will cancel out. And then on the right side, 0 divided by R is still 0. So that will at least get rid of all of the R, and we don't even need to worry about the value of R. We know the value of R, it's 8.31 joules per Kelvin mole. But by dividing both sides by R, it means we don't even need to know the value. Is there anything else that shows up in every term that we could get rid of? Any numbers or units of measurement? Yeah, there's a moles in every term in terms of the units of measurement. We could divide both sides by moles. That way moles, and again, this divisor distributes to both terms. So moles cancel out, and then 0 divided by R times moles is still just 0. And yeah, there's a 1/2 in every term as well. We've got a 6 divided by 2, a 7 divided by 2. We can cancel out divided by 2 by multiplying by 2. So let's try multiplying both sides by 2, as well as dividing by R times moles. That way, when we multiply, again, that distributes to both of these terms. So the times 2 cancels out this divided by 2, and also this divided by 2. And on the right side, 0 times 2 divided by R moles is still just 0. So we should get, canceling out the 2, the R, and the moles, we just get 6 times 3 times T final minus 373 plus 7 times 2, because we're canceling out the divided by 2 and canceling out moles and canceling out R, times T final minus 600 kelvins equals 0. We can simplify that further. 6 times 3 is 18. 7 times 2 is 14. And what else could we do here? If we want to solve for T final, what would be a good next step? Yeah, let's go ahead and distribute these. Although before we do, another step that might make the numbers a little easier to work with. What are 18 and 14 both multiples of? Yeah, those are both multiples of 2. So before we distribute, just to make the numbers a little easier to work with, let's also divide both sides by 2, which I guess will just cancel out the times 2 we had already. So we'll not divide by, or we'll not multiply by 2, we'll just multiply by 1 over r times moles. So we're effectively dividing both of these coefficients by 2. 18 becomes 9. 14 divided by 2 becomes 7. Again, not really necessary, but just to make the numbers a little easier to work with. At this point, let's go ahead and distribute that. 9 times T final minus 9 times 373 plus 7 times T final minus 7 times 600 Kelvin equals 0. And at that point, what can we combine? Yeah, if we combine the T final terms, because we've got 9T final plus 7T final, we can factor out T final and just get T final times 9 plus 7. So that's a total of 16 times T final. And yeah, these numerical terms, 9 times 373 and 7 times 600, we could combine. That sounds like it's probably going to be a calculator step just because the numbers are going to be pretty big. But before we even multiply those together, we want to get rid of them ultimately. We want T final on one side by itself. So how do you get rid of minus this big number and minus this big number? What's the opposite, for instance, of subtracting 9 times 373? Yeah, so we just add 9 times 373 to both sides and add 7 times 600 to both sides. And those are both in Kelvin, so we can factor out the Kelvin. A unit of measurement can effectively be treated as a multiplier, a variable multiplier. It's just that instead of representing some number, it represents some amount of temperature or some distance or something like that. And then algebraically, what's the last step for solving for T final? What's the one last thing we still need to do? Yeah, divide both sides by 16. So that is expression for our answer. 9 times 373 plus 7 times 600, all divided by 16. At this point, let's go ahead and punch that into a calculator. So in parentheses, 9 times 373 plus 7 times 600, end parentheses, divided by 16. And I'm getting 472. So final temperature is about 472 kelvins. And quick reality check, how does that compare to the initial temperatures of both of the substances? If we started off with A at 373 and B at 600, does it make sense for them to both end up at 472? Yeah, because before we even calculate that, before we even run the numbers, if we got one cold substance at 373 and one hot substance at 600, what do we know? What's the one thing we know for sure about the final temperature? Before we even do any calculations. Yeah, it's not necessarily exactly in the middle, like the average, but it's somewhere in between. So we at least know the final temperature is going to be somewhere between 373 and 600, and 472 is indeed somewhere between 373 and 600. So this at least passes the first reality check of, yes, it is within this range. It's between the coldest temperature and the hottest temperature in the system, which is what we should expect. If we had gotten some temperature that's hotter than 600 or colder than 373, that would immediately mean something has gone wrong and we should go back and check all the steps. But 472 definitely sounds realistic. I think that should do it then. That is final temperature, which is exactly what we were looking for. And on the way, we figured out even the initial temperature of B, even though that wasn't given. And then once we had all the initial information, we could fill that into conservation of energy to find the final equilibrium temperature. Any other questions on that one? In this setup, it looks like we've got a graph of distance, presumably distance between atoms, two atoms, and energy. And yeah, we want to find the potential energy. So presumably, since this is a Lennard-Jones potential, this is going to be the standard Lennard-Jones potential energy shape. The characteristic vertical asymptote, then a swoosh through a minimum, and then curving up towards a horizontal asymptote. But I think we're going to need to figure out some more information here. We have a graph of kinetic energy. And we want to graph potential energy. What information do we have here? Or what other information do we know based on the potential energy? First of all, if we know the basic shape of potential energy, yeah, I think the total energy, I mean, based on the fact that the potential energy graph should look something like this. We just need to figure out where it's going to hit its minimum, what the asymptote is going to be, maybe some other points. How do we find the total energy here? If we don't even have a potential energy graph shown on this graph yet, are there any values of potential energy that we do know for sure? Yeah, we do know the maximum kinetic energy. It looks like kinetic energy maximum is, looks like 0.8. And that's in units of epsilon. Let me go get an epsilon. Epsilon. So the kinetic energy maximum is 0.8 epsilon. And we can find total energy if we know the potential energy at that instant, because we know total energy is kinetic energy plus potential energy. What should be the value of potential energy when kinetic energy hits its maximum? At that same instant in time. So presumably at this location, this R value. What should be the value of potential energy there? It's not going to be 0. It's going to be a lot lower than that. What is the lowest potential energy you can get on the Lennard-Jones graph? Yeah, -1 epsilon. The lowest potential energy minimum on the Lennard-Jones graph is -1 epsilon. So we at least should have that as a data point, assuming that this epsilon really does represent the well depth as it generally does. We should expect a low point at -1 epsilon. It's not so much a general rule so much as just what we mean by epsilon. When we talk about epsilon in these cases, we usually mean as just as a standardized meaning of the variable. Epsilon typically means the well depth. That is the energy associated with one pair bond. So I would assume that minimum potential energy is -1 epsilon by definition of epsilon, assuming we're using the standard meaning of that symbol. And the maximum kinetic energy and minimum potential energy should occur at the same location, because when kinetic energy reaches its highest, that's because potential energy has lost as much as it can. And if we fill those into the E total equation here, E total is the kinetic energy at any location really, plus the potential energy at the same location. If we add those up, what do we get? Yeah, so that's the total energy. Total energy is -0.2 epsilon. And assuming this is a closed system, which it should be, total energy should be constant. So what would total energy look like on the graph here? What does a constant function look like on a graph? Right, specifically a horizontal line, and not at +0.2, but yeah, -0.2. So a horizontal line at exactly -0.2 as the energy level. So this horizontal is the graph of E total. This constant value. So we've got the entire graph of E total. We were provided with the total graph of kinetic energy. We have one data point on potential energy. Are there any other values we can now fill in for potential energy? We've got potential energy minimum right here, -1 epsilon. Kinetic energy doesn't really, or sorry, potential energy doesn't really have a maximum though. Because if you take a look at the potential energy graph, the standard Lennard-Jones potential energy graph, this side of the graph just keeps going up and up and up. So it doesn't really have a maximum value. Its maximum value would be infinity, if you even call that a maximum value. So there isn't really a PE max on the graph. But there is one important high value we could find. What's the lowest kinetic energy can get? Yeah, there are, and it looks like in this case, there are two locations where kinetic energy happens to be 0, here and here. So those R values, those distances, we would usually call R min and R max. That is, R min is the closest the particles can get to each other, and R max is the furthest the particles can get from each other. The particles can't get closer than this and can't get further than this. They're just going to oscillate between those two distances, close together, far apart, R min, R max. So at those two locations, kinetic energy is 0. And going back to the E total setup, if kinetic energy is 0, what does that tell you? If kinetic energy is 0, then what does that tell you? What's left in the equation? Well, remember, potential energy is not, oh yeah, in this case, potential energy at that location is -0.2. Generally, if kinetic energy is 0, then potential energy is E total, at least at that location. And yes, that's correct, that is -0.2. So we at least know, not everywhere, but at these two locations, at this location and this location, the potential energy has to be the same value as E total. So that gives us 2 more data points on our graph of potential energy. At this location, R min, potential energy is -0.2. At this location, R max, potential energy is -0.2. It's not so much an assumption of potential energy being -1. It's that -1 epsilon is, or negative epsilon is just what we call the lowest potential energy. Potential energy on the Lennard-Jones system has a certain lowest value. We call that value negative epsilon. And epsilon presumably represents some tiny number of joules. Maybe this minimum value is -3 × 10 to the -20th joules. Or maybe it's -5 × 10 to the -21 joules or something. Whatever that tiny value of energy is, we call it negative epsilon. So negative epsilon just represents the value of the minimum potential energy. Yeah, if we're using this standardized notation, epsilon means the depth of that energy well, that low point of energy. And sometimes if we're talking about like comparing several different types of particles, we might use epsilon to represent the well depth of one of the types of particles, and then the other one will have a well depth represented as some multiple of that. Like maybe we'd say one of them has a minimum potential energy of -1 epsilon, and the other one has a minimum of -3.5 epsilon or something. But that's just relative to the epsilon of the other one. But I think with those 3 data points, and also the information that it should approach zero as an asymptote, I think we should be able to draw in the rest of the graph. First of all, we should expect the kinetic energy to be a mirror image of a portion of the potential energy graph. So we can use that fact that we know if we trace out the kinetic energy graph, the potential energy graph, or the kinetic energy graph, should be an exact mirror image of the kinetic energy graph, or other way around, but mirror image and shifted. So we know that at least a portion of the potential energy graph is a mirror image of the kinetic energy graph and shifted. And then I think we can draw in the rest, because we know as we travel further and further to the right, larger and larger R, what should we expect to happen to potential energy? What would that potential energy approach as we get to further and further out in the R direction? Negative 0.2 was its value at this one location. But as we go further and further, yeah, it should approach zero. The potential energy curve should approach an asymptote of zero, getting flatter and flatter, closer and closer to zero as we get further and further out. Because remember, the slope of this graph represents the force between the particles. As the particles get further and further from each other, they experience weaker and weaker attractive force. So that means the slope of this graph should get closer and closer to flat. Meanwhile, as we go to the left, what's going to happen? What should we expect this curve, this portion of the curve, to do? Yeah, it's going to go up. And also it should be getting steeper and steeper and steeper, on the grounds that as the particles get closer, they repel, and the repulsive force becomes stronger and stronger and stronger. So this part should just get steeper and steeper and steeper. Something like that, probably even steeper than that. Let me adjust that a little bit. Something like that. So this gives us a very good, very accurate sketch of the potential energy graph, based on the minimum that we know it should have, these two data points we know it should go through, and the asymptotes we should expect it to have. Any other questions on that? And or any other topics you'd like to work on? Let me go check that. Practice final 2. Could you send me a copy of that one in the chat, just as a file, and I'll take a look at that. In the meantime, let me pull up that Coyote problem. So here it looks like the Coyote is launching from this spring, and we know the spring constant, the ground is completely flat, but we do have friction. And the friction is causing snow to melt. And we want to know how far does the spring need to be compressed in order to just barely reach the 50-meter mark where the Roadrunner is. And I think conservation of energy would be a good approach here, because we know that we have several quantities changing that are all indicators for energies we already know about. Specifically, if we go from launching from the spring to just barely reaching the Roadrunner, what kinds of energy should we expect to be changing? if you compare the initial situation, just launching from the spring, to the final situation, reaching the Roadrunner, what kinds of energy would be changing from start to finish? Or what values are changing that are indicators for certain types of energy? Specifically, what kind of potential? Yeah, spring potential, I think, is going to be a good thing to start with here. In fact, in general, if you're not sure what kinds of energy are changing, it might be a good idea to just make a list of all the types of energy we've seen in this class so far, because there aren't all that many types. I think we've only really covered like 6 types of energy. And then ask yourself, is the indicator for any of these changing? So if you consider, for instance, we've seen thermal energy, bond energy, chemical energy to some extent, kinetic energy translational, kinetic energy rotational, potential energy of spring, potential energy of gravity. I think that's it, unless you get into the individual molecular stuff. So of these, we know spring potential energy is changing because there is a spring being compressed or stretched. So definitely we want to include spring potential energy. Are any of the other of these changing, or are there any indicators that suggest that one of these is changing? What else is happening here that might be related to one of these energies? Yeah, friction is definitely, well, friction is really a force, not an energy, but it is causing a transfer of energy, specifically a transfer of energy to what? What is friction actually doing here? Is the friction causing temperature to change? What specifically does the problem say is happening as a result of that friction? Yeah, snow is melting. So that's technically not thermal energy. That's, yeah, bond energy. I think we're assuming here that the ice is already at the melting point, because it doesn't really say anything about the ice warming up. It just says it's melting. So I would assume that the ice is already at the melting point and friction is causing an increase in bond energy as the ice melts. I don't think anything's really changing temperature, so we can ignore thermal energy. Doesn't look like there's any chemical reactions happening, so we can ignore chemical energy. Is there any change in translational kinetic energy from start to finish? Do we know anything about the starting speed of the Coyote and the ending speed of the Coyote? If you're launching yourself out of a spring like this, what's your starting speed just before you launch? Yeah, we can assume the Coyote starts with speed 0. And if we want to assume he just barely reaches the Roadrunner, what's his final speed? Right, also 0. Because if by the end he's still in the process of moving, that means he compressed the spring more than he strictly needed to. We want to figure out the just barely case. So since the starting speed and ending speed are the same, what's the total change in translational kinetic energy? Yeah, that should also be 0. Even though he's in the process of moving, there's certainly kinetic energy in between, but there's no overall change in translational kinetic energy. So we can ignore translational kinetic energy here as far as the delta is concerned, because initial and final values are the same. There's no overall change. And nothing's really spinning, so we can ignore rotational kinetic energy. We already addressed that, yes, there will be spring potential energy. Is there any change in gravitational potential energy? Is he changing height from start to finish? Or changing altitude? Yeah, it says this is a flat slope. So presumably there is no change in elevation, and that means no change in potential energy of gravity. It looks like in this entire process, the only things changing are the spring potential energy is changing, because presumably we're going from a compressed spring to a spring back at equilibrium. And yeah, and then also we are melting some snow as he travels. So I think we can assume that those are the only changes. Change in spring potential energy plus change in bond energy. And what should we expect those to add up to? This is the change in total energy is both of these combined. But what can we expect the change in total energy to be? Is there any change in total energy? Should we treat this as a closed system with no change overall, or an open system where there's some change? Or how would we be able to tell? Is there any energy entering or leaving the system during this process of motion? Or anything in this that specifically suggests it might be an open system or closed system? I notice this does mention there's friction, and we often treat friction as a process of energy leaving the system. But in this case, what's that friction turning energy into? Friction is causing energy to be transferred to what? What's that friction making happen? Strictly speaking, I would call it work rather than heat, because work is a transfer due to a force on a moving object. So friction is a force that involves work, not heat. Not thermal energy in this case, because it doesn't say anything is getting warmer. What's happening instead? What's friction actually doing? What's the one thing this paragraph says about what friction is doing? Yeah, due to friction, the snow melts. So friction is actually causing a change in what kind of energy? Right, friction is causing a change in bond energy, which we are including in our equation. The important thing about whether it's an open or closed system is whether we're including all the types of energy that are influencing each other. Spring potential energy is changing because there's a spring being stretched or compressed. Bond energy is changing because the snow is melting. Those are the only things interacting. The system is the Coyote is losing energy due to friction, but that energy is transferring to melting the snow, and we're including that in our equation as delta E bond. So because we're including what the energy is being transferred to, this does count as a closed system. And in a closed system, what's the change in total energy? Right, the total change is 0. So we can treat this as a closed system because even though there's friction causing a transfer of energy to delta E bond, we are including that delta E bond as part of our system. And ultimately, the only difference between an open system and a closed system is, are you including everything? In this case, we are including everything that's changing as a result of this process. So this is a closed system. There's no energy coming in or leaving from outside because we're only talking about transfers of energy between systems that we are including, or types of energy we are including. Any questions on that setup so far? And what formulas could we use here? What's our usual formula for delta spring potential energy, for instance? Or what is the indicator for spring potential energy? What should spring potential energy depend on? Yeah, the usual formula for spring potential energy is half the spring constant times change in x squared. And I would actually put the x squared in parentheses like this, just to emphasize that you're taking the squared x values and taking the difference in squared x values. So like the squared value of x final minus the squared value of x initial. So I would put these squared inside the parentheses to emphasize that the squared is done first, and then you take the difference of the squared values. So the spring potential energy, half the spring constant times, and we could even expand that as x final squared minus x initial squared. Plus, what about delta E bond? How could we write out or what's the usual formula for change in bond energy? Or what determines how much energy it takes to melt something? Yeah, and actually we don't even need the plus or minus an absolute value. We could just write this as delta mass times delta H, where delta mass actually means a change. It means the amount of mass that's changing phase. Delta H isn't really a change in something. Delta H is just a constant associated with the material. In fact, a lot of textbooks don't even call that delta H. They just call it L for latent heat. Latent in the sense of hidden within it, the heat that's hidden within it because of its material. But delta M times this property of the material, which you could call the heat of melting or the latent heat of melting, whatever you want to call it. So let's fill that in. We've got delta M times L for the snow melting, and those have to add up to 0. We also know some of these values. K, the spring constant, is given. That was the 300 newtons per meter. And do we know either of the distances? Do we know the final amount the spring is compressed, or do we know the initial amount the spring is compressed? Do we know either of those values? If we're assuming that the initial time is when he's just about to launch from the spring, do we know how much the spring was compressed at that instant? Do we know the original compression of the spring? Or is that what we're trying to find? Yeah, we don't know that. In fact, that's really the end goal here. The goal is how we want to know how far do you have to press in the spring. So x initial is the unknown. So if we were to make a list of what we know and what we're trying to find, I think the initial and final values of most of these variables would be known, but the initial value of X, the initial compression of the spring, that's the unknown we're trying to find. This is our what we want list. So we want to know X initial. How far was the spring compressed at the instant we launch? But at the end, after the Coyote gets launched, what's the final compression of the spring? If you take a spring and press it back and use it to launch something, after you launch it, how much is the spring compressed? Yeah, it's not compressed at all. There's no compression. So we know that X final is 0. After the launch, spring is no longer compressed. Not compressed or stretched. So X final is going to be 0. In fact, we could fill that in now. X final is just 0, so we'll fill in a 0 here. So we've got K over 2, and we know K. We may as well fill that in as well. 300 newtons per meter divided by 2 becomes 150. Times 0 squared is just 0, minus X initial squared is negative X initial squared. Plus, and what about delta M? Do we know how much snow melts? Does this tell us anything about how much snow melts? .3 grams, does it just melt 0.3 grams in total? Or is that 0.3 grams of snow melted per what? Yeah, 0.3 grams of snow melt every meter. But how many meters is he actually traveling? Right, he's traveling 50 meters. So we can combine those. We know that we are melting 50 or 0.3 grams of ice per meter of travel. How would we combine that with the 50 meters to get the total amount of ice melted? What would we do with those numbers, the 0.3 grams per meter and the 50 meters? Yeah, we can multiply those. If we multiply 50 meters times 0.3 grams of ice melted per meter, what happens to the units when we multiply those? If we're multiplying meters times grams per meter, one of the meters is in the numerator and the other is in the denominator, though. So they're not going to combine. What's going to happen instead? Yeah, they cancel out. We got times meters and divided by meters. Right, we just get grams of ice melted. And 50 times 0.3 is the same as 5 times 3, so that'll be 15. So 15 grams of ice melted in total. Over the course of this entire journey, he melts 15 grams of ice. So that'll be delta M, 15 grams. Also, in terms of positive versus negative, we're changing 15 grams of ice into 15 grams of liquid water. And generally for the indicator, we use the mass of the higher energy state. Would you say ice or liquid water is higher energy? Yeah, liquid is the higher energy state. And are we gaining 15 grams of liquid or losing 15 grams of liquid? Yeah, we are gaining 15 grams of liquid water. So we'll say delta M is positive 15 grams. On the other hand, if it was freezing, like we go from some water to less water because it's turning to ice, we'd be losing liquid, so that would be negative 15 grams. But the delta M, we're essentially taking final amount of the higher energy state minus the initial amount of the higher energy state. We end with 15 grams of water. We started with 0 grams of liquid water. So final minus initial would be 15 grams of liquid minus 0 grams of liquid. That delta is positive 15. So delta M is positive 15 grams. And what about the latent heat for ice melting? Do we have that information for ice? Was that provided anywhere? Oh yeah, if we look up here, we've got, delta H melt, presumably for water, is 333 kilojoules per kilogram. And they point out this is the same as 333 joules per gram, because kilo just means 1,000. If you got an extra times 1,000 in the numerator and an extra times 1,000 in the denominator, you could cancel those out. The Ks, the kilos, can cancel out. So we could just say 333 joules per gram, which I think might be easier because then we can cancel it out with the grams that are already here. And also joules is useful because the other value will be in joules as well. So if we just write the latent heat as 333 joules per gram, then in that case, grams and grams cancel out. So we just get 15 times 333 joules. Also here we've got newtons per meter being multiplied by a distance squared. Distance is measured in meters. So when you square it, you get meters squared. That cancels out one of the meters and we're left with newtons times meters, which is the same as joules. So everything here is going to work out to joules in the end anyway. Simplify this a bit, we get negative 150 times x initial squared plus 15 times 333 equals 0. And at this point, I know everything's in joules. I know x is going to end up in meters. So at this point, I'm going to go ahead and leave off the units. Usually, I would recommend keeping the units just to be on the safe side and make sure you get everything matching up. But if you already know all the terms match up with the same units and no conversions are needed, and you already know that what units the final result is going to be in, it's generally safe to leave those out. What else do we need to do here? What's going to be our last couple of steps for isolating x initial? Algebraically, how would we get x initial isolated here? Yeah, let's say subtract the 15 times 333. And you don't even have to multiply those together yet. You could just leave it as 15 times 333. So negative 150 times x initial squared equals negative 15 times 333. And then what? Right, then divide by negative 150. So x initial squared equals, the negatives cancel out. We get 15 times 333 over 150. And 150 and 15 can reduce to what? What's 15 over 150? Right, that reduces to just 333 over 10, because 15 over 150 is the same as 1 over 10. And what is 333 divided by 10? Yeah, 33.3. So x initial squared is 33.3. What's the last step we still need to do to find x? Yeah, square root. So that'll be somewhere between 5 and 6, specifically 5.77. So that's the compression. You're going to need to compress the spring almost 6 meters and then launch it. So a huge amount of compression. Any questions on that? All right, we are out of time, but if you have any other questions, let me know on Discord. I'll be having office hours over the next few days as well. I'll post the schedule for that on math.nchoose.org. But good luck on finals. Have a good break, and I hope to see you next quarter in Physics 7B. You're welcome.